To the untrained eye, the modern aviation engine is an aesthetic contradiction. Look at the wing of a modern wide-body airliner. The engines are no longer sleek, cigar-shaped tubes tucked neatly against the fuselage. The diameter of a General Electric GE9X engine is roughly equivalent to the entire fuselage width of a Boeing 737. It is a structure so vast that a professional basketball player could stand inside the inlet and barely touch the rim.
Intuition screams that this is wrong. Common sense dictates that in aerodynamics, size equals drag and weight equals fuel burn.
We are taught that to go fast, things must be small, sharp, and needle-like.
Yet, the engineers pushing the boundaries of thermodynamics have doubled down on size. They have made the engines wider, heavier, and more imposing. This brings us to the great paradox of modern aerospace engineering. To save fuel, we must burn less. But to burn less while moving 300 tons of aluminum at nearly the speed of sound, we are not making engines larger for vanity.
We are making them larger because of a fundamental law of physics that dictates the relationship between mass, acceleration, and kinetic energy.
We are witnessing the triumph of the High Bypass Turbofan. To understand why bigger is not just better, but scientifically mandatory for efficiency, we must shrink ourselves down to the molecular level. The journey begins at the intake. Before the air even touches a metal surface, it is being coerced.
The massive front fan, spinning at thousands of revolutions per minute, creates a zone of low pressure so intense that it vacuums the atmosphere into its maw.
This is not a gentle breeze. This is a suction force capable of emptying an Olympic-sized swimming pool of air in less than a second. The first component we encounter is the fan blade. On the GE9X, there are only 16 of them.
In the past, engines had 30 or 40 titanium blades, heavy and dense. But as engines grew, titanium became a liability.
A solid titanium fan of this diameter would be so heavy that the centrifugal force, the outward pull, The engineering solution was to abandon metal for the blade structure entirely. These blades are sculpted from carbon fiber composite. Visualize the manufacturing process. It is a work of slow, agonizing precision. Thousands of layers of carbon fiber tape are stacked, injected with a proprietary resin, and baked in an autoclave until they fuse in. But carbon fiber, while strong, is brittle. It cannot withstand the impact of a bird strike or a hailstorm at 500 miles per hour. Therefore, the leading edge, the sharp knife point that slices the air, is clad in a sheath of high-grade titanium, and the trailing edge is reinforced with steel.
The result is a blade that is lighter than aluminum, yet stronger than steel.
Curved in 3 dimensions to bite into the air like a twisted wing. As the fan spins, the tips of these blades are traveling faster than the speed of sound. They are creating continuous, localized sonic booms. The curve of the blade is designed to manage these shock waves, forcing the air backward rather than letting it pile up in a wall of pressure. Here lies the secret of the bypass ratio. In this massive engine, the air is divided onto 2 distinct paths. This is the fork in the road that defines efficiency.
10% of the air, the core airflow, is destined for the center of the machine. It enters the compressor,
that act like a progressive trash compactor. The other 90% of the air, the bypass airflow, never touches the fire. It is pushed around the outside of the engine core, through a duct, and ejected out the back. This is where the physics of propulsion becomes counterintuitive. Thrust is generated by taking a mass of air and accelerating it. Newton's second law tells us that force equals mass times acceleration.
You can get the same amount of thrust by taking a small amount of air and accelerating it to violent, supersonic speeds.
Or you can take a massive amount of air, a huge M, and accelerate it only slightly. The problem with the fighter jet method, high acceleration of small mass, is kinetic energy. Kinetic energy increases with the square of velocity. If you double the speed of your exhaust, you quadruple the energy required to produce it. That is wasted fuel. It is energy spent making the air move fast, rather than making the plane move forward.
By using a massive fan to move a gigantic volume of air at a slower speed, we minimize the wasted kinetic energy in the wake of the aircraft.
This is why the engine must be huge. The bigger fan allows us to grab a larger cylinder of the atmosphere. It allows us to increase the mass part of the equation so we can decrease the velocity part, maintaining the same thrust while burning significantly less kerosene.
But to turn that massive fan, we need power, titanic amounts of shaft horsepower. And that power comes from the
Follow that 10%. It enters the high-pressure compressor. This is a series of 11 rotating discs, each smaller than the last.
The air is not just squeezed, it is assaulted. The pressure ratio in modern engines approaches 60:1. That means the air molecules are packed 60 times tighter than they were in the open atmosphere. When you compress a gas violently, you are fighting thermodynamics.
By the time the air reaches the end of the compressor, it is searingly hot, reaching temperatures of over 600.
It is pushed into the combustor. This is the heart of the beast. In older engines, fuel was dumped in and burned, creating a jagged, uneven flame. In the pursuit of efficiency, we now use a lean burn system. The fuel nozzles are not simple pipes. They are complex 3D printed labyrinths that swirl the fuel and air into a microscopic mist.
The mixture is kept lean, meaning there is an excess of air relative to the fuel. This lowers the peak temperature of the flame just enough to prevent the formation of nitrogen oxides, harmful pollutants, while extracting every joule of chemical energy from the kerosene.
The environment inside the combustor is apocalyptic.
Temperature soars to over 2,400 degrees Celsius. This creates a critical materials engineering crisis. 2,400 degrees is far above the melting point of the metal alloys used to build the engine.
If we built the combustor out of standard steel or even titanium, it would turn into a liquid puddle in seconds.
The breakthrough here is ceramic matrix composites, or CMCs. We have moved beyond the age of metals. We are now in the age of advanced ceramics.
These materials are made from silicon carbide fibers embedded in a silicon carbide matrix. They are essentially a high-tech weave of stone.
They are 1/3 the weight of metal, but more importantly, they can withstand temperatures that would destroy the strongest superalloys on Earth. By lining the combustion chamber with these ceramics, engineers can run the fire hotter.
And in thermodynamics, a hotter fire means a more efficient expansion of gas.
Now, the superheated, high-pressure gas is unleashed. It slams into the high-pressure turbine. These are the blades that extract the energy to drive the compressor.
They are the most stressed mechanical components in human history. Each turbine blade is a single crystal of nickel-based superalloy. They are not cast in a mold in a traditional. They are grown in a vacuum furnace, slowly pulling the molten metal away from a seed crystal so that the
But even a single crystal cannot survive the 2,000-degree firestorm without help. The blades are perforated.
Cool air bled from the compressor before it was burned
is pumped into the hollow center of the blade and forced out through these holes.
The blade is essentially flying inside its own localized atmosphere, surviving in an environment that should physically incinerate it.
After the high-pressure turbine extracts energy to keep the compressor spinning, the gas still has energy left. It flows into the low-pressure turbine.
This is the final energy transfer.
The expanding hot gas spins the low-pressure turbine, which spins the shaft, which torques the massive carbon fiber fan at the front.
The thermal energy of the burning kerosene has been transmuted into the mechanical energy of the fan.
The exhaust from the core shoots out the back, hot and fast. But it is immediately surrounded by the blanket of cold, bypass air from the fan.
The mixing of these two streams, the violent hot core and the massive, slower bypass column, creates a shear layer.
Engineers spend lifetimes optimizing the nozzle shapes, adding serrated edges called chevrons to blur the boundary between hot and cold air.
This mixing not only aids in thrust efficiency, but dramatically reduces the noise footprint, turning a roar into a hum.
So, we return to the exterior view. The paradox is resolved.
The engine is huge because it acts as a gear reduction for air.
It takes the high-intensity chemical violence of the core and leverages it to push a massive wall of air gently.
But the mathematical gain in propulsive efficiency provided by the high bypass ratio completely eclipses the drag penalty.
Every millimeter of that diameter represents a victory over the tyranny of the rocket equation. By embracing size, we reduce the velocity mismatch between the jet exhaust and the still air.
The GE9X and its kin are not just engines. They are equilibrium machines. They balance thermal limits against material science, aerodynamic drag against propulsive thrust, and centrifugal destruction against structural.
To keep deconstructing the world's most complex systems, stay connected to Gridonix.